Greetings. Dr. Martha Conklin is Professor of Engineering and a member of the Environmental Systems Graduate Group at UC Merced, where she was part of the founding faculty. She is currently Interim Director of the Sierra Nevada Research Institute and Director of the Merced Natural Reserve System. Her research has focused on groundwater-surface water interactions. With that, I'll turn it over to you, Martha.
Great. Thank you, Richard. I'm very pleased to be here to present this webinar. I'll be talking about water yields in forest management, a case study. This has been a truly interdisciplinary panel that we've been involved in, and I hope you'll learn something as you listen to me. Just a brief overview of how I'm going to structure this, I'm going to talk about the project background, the SNAP project, the field research that we did, and then the two scales of modeling that we are doing to understand our results. Starting with the project background, I want to talk about the Sierra Nevada Adaptive Management Project. This is a joint effort by the UC California state and federal agencies to study the current management practices of the Forest Service in forest lands of the Sierra Nevada. To approach this, we have a multidisciplinary team looking at the stakeholder response to proposed management actions, evaluating the forest and health, a spatial team which integrates across all scales and all the teams, and then I'm the PI in the water team, which is looking at both what the effect of these management decisions have on water quantity and quality. And coupled with all this is looking at the impact of these managements on some of the keystone species. We have an owl team for looking in the north, and the fisher team looking in the south. We have two sets of field sites that we're looking at. We designed this experiment so we would have before and after and controls on this. So for the water team approach, we measure the water balance, the water quality components, both before and after the forest treatments, and we also have, as I mentioned, a control and a treated catchment. Then we're modeling the headwater processes and trying to estimate what water yields would be given projected forest densities. And then we are upscaling because our headwater catchments are about 1 to 2 kilometers, square kilometers in size, and we want to transfer up to larger watersheds, which are maybe 40 kilometers squared. Our two study sites, as I mentioned, we have a northern site and a southern site. One is what we call the last chance, because that's the timber harvesting name in Tahoe National Forest. And our study sites drain into the American River. And our two study basins, you can see in the top map on the right-hand side, are Bear Trap Creek, and that's a treated aquifer, and then our treated watershed, and Fraser Creek, which is our control. And then down south in the Sierra National Forest, we have what we call the Sugar Pine Project, and we have two catchments there. You can see them. They're on the lower map on the upper side of the digital elevation model, and it shows Big Sandy Creek and Speckerman Creek. In this case, Big Sandy Creek is the treated catchment. Here you can see our catchments in a little more detail. You'll note how small they are. They're typical headwater catchments, about somewhere between 1.4 to 2.4 square kilometers in size. We picked them, we tried to match them as closely as we can in terms of elevation, size, aspect, and slope. They're located inside fire sheds, which vary between 20 to 24 kilometers squared. And while our headwater catchments have perennial streams and tend to be higher elevation, the watershed elevations are stretched between roughly about 1,800 meters, 1,800 feet to about 6,500 feet in elevation. The forest treatments were planned before we even started this study. They're called SPLATs, strategically placed landscape treatments, and they involve different types of treatments: underburning, tractor thinning, as well as cable thinning. And what I show here is what the SPLATs are on the American Basin one. And to the right is just a picture of what the landscape might look after mastication. To do our field methods, we worked on getting spatially distributed measurements throughout our catchments. In each catchment, for each pair of catchments, we had two MET stations, one at the bottom of the catchment and one at the top of the catchment. We put sensors around the water, each MET station or meteorological station, trying to capture aspect by looking at north and south facing slopes. We distributed about 62 snow depth sensors and about 164 soil moisture sensors. These are around the MET station and also on the slopes inside our watershed. We had 4 stream stations where we measured both discharge and sediments. We measured sediments using a load cell to measure bed load movement and turbidity as a proxy for suspended sediments. Here's our preliminary water yield results, and these are for the 4 years of measurements that we had. What we have plotted here is the amount of flux on a yearly basis in centimeters for the 4 different water years, which are on the x-axis. The northern site, Last Chance, is in the top graph, and the southern site, Sugar Pine, is in the bottom sets of graph. And the dotted line indicates when the treatments occur. You can see that we get slightly more precipitation in the northern sites than we do in the southern sites. And the response to the precipitation was fairly consistent for both sites with our treatment discharge, even though it was untreated. So our Fraser Creek in the northern site having slightly less discharge than Bear Trap. And then in the southern site, seeing that Big Sandy had slightly more discharge than Speckerman in the southern site. Unfortunately for our study, the treatments occurred between 2 extreme drought years. So in the northern site, you'll note that we still have that slight same type of behavior with slightly more discharge from the control site than the treatment site. That seems to not be evident on the treatment, but it was such a drought year, it's going to be difficult. We haven't tangled that quite yet. And if you look at the southern site, you'll notice on the water year, the drought year 2012, we saw no difference in behavior between the 2 sites, and pretty much the same for 2013. So the drought seemed to trump any effect of the treatment. Although we did get slightly, you might argue there's a slight decrease in the treated basin, but I think that's in the noise. Looking at our suspended sediment results, basically we seem to be in a sediment limited creeks in terms of it. For the period of the study, most of the suspended sediment seemed to come from within the creek. We saw fine settlement accumulating during low base flow periods. We did both with surveys, we observed it. And then when we started having high flow events, typically in the fall, the first storms, we saw that sediment being washed out. So even though in the fall we did not have high flow events, we ended up with most of the flow events having turbidity in them. And then as the number of high flow events increased from midwinter to snowmelt time, the number of those events with a large amount of turbidity decreased. Looking at our bed load movement, we basically, it seems as though we have a step topography in our streams where you have steps and pools. And watching, what we saw moving in it was mainly mostly sand. And that seemed to have a conveyor belt type of model where you would have a vent and the sand would move, be deposited, and then continue moving down this. So if we look at the graphs below, which is on the x-axis is time, and on the y-axis is the amount of sediment that we're seeing move down the stream, you'll note that there'll be a storm event. We see some increased amount of bed load, and it slowly is eroded away. You have a next storm event, you see some deposition, and that can slowly be eroded away back to the baseline, implying that we have a fairly, our streams seem to be at equilibrium with the amount of bed load moving down them. So let's get into the modeling in terms of looking at how we're going to take our various data and actually put them in a framework where we can start teasing out how the water is moving through the system. If you look at the picture I have on the left is a picture of a mountain stream with snow, and I'm showing the various fluxes that you might think that occur in the landscape in our conceptualization. We can have, obviously you have your inputs, would be your precipitation. Typically in the wintertime it's snow. And then you have and I'm going to look at inputs into the stream as that. So, and then you have what leaves the system, and that would be the evapotranspiration. That would be evaporation. If there's liquid water, and transpiration from basically the trees respiring, and then you have sublimation from the snowpack. As the snow melts, it infiltrates into the groundwater, as well as it melts and runs into the stream. And then we have the discharge or runoff that comes off of it. And as will be interchange between the groundwater and surface water. Those look fairly straightforward when you look at that. If we think about them in terms of a model, what we end up doing is we're using RESIS as a model that breaks the landscape up into certain features and then works at having water move through the system and basically having different processes occurring, such as snow accumulation and melt, snow melt going into the porous medius or the subsurface, and then looking at how we get the efficiency of drainage coming off on it and looking at all the interactions between that, and then what actually comes out of the stream at our where we're measuring it, and we call that response the hydrograph, in which we look at discharge versus time. There's a number of, the model we're using is RESIS, the Regional Hydroecological Simulation System. It has a variety of inputs that go in, precipitation, temperature, relative humidity, vapor pressure deficits. The vapor pressure deficit and the relative humidity help us determine the evaporation and transpiration that's occurring. We have spatial inputs. We've had LiDAR flights, so we have fairly detailed elevation maps and vegetation maps that our spatial team has developed, as well as we're using soil maps to determine the properties of soil. Um, and these are all layers that we put into the model. And then outputs, we get snowpack distribution, the amount of water in the storage, and the yield that comes out of the watershed. It's taken us quite a while to calibrate our model. We have not simply calibrated it on just at discharge at our at the places where we're measuring discharge. We've also calibrated it using our spatially distributed snow accumulation measurements. So we have that spatial distribution in the model. And we've also calibrated it relative to the response of our soil moisture probes. So we have calibrated with 30 plus observations of snow depth plus 80 or so observations of soil moisture, as well as our stream discharge measurements. We've we've applied, now that we have a well-calibrated model, we're working on developing modeling scenarios to consider both fuel treatments and the effect of wildfire on these catchments. One of the fuel treatments we're very interested in vegetation reduction, and we can scale it to different fuel densities. If we think about vegetation reduction to wildfire, we just have to superimpose a burn intensity pattern, because the vegetation reduction will be much less uniform. We look at snow albedo, and in both cases we're assuming it's comparable, whether it's going to be due to vegetation reduction or and we assume it will be for wildfires, it will be decreased for several years after fire burn due to the soot. We have in soil moisture, wildfires, we expect a decrease in soil moisture because of surface hydrophobicity. And in soil moisture after fuel treatments, if there's nothing done to re-aerate the soil, soils will be compacted and we expect reduced storage. Litter cover, and that turns out to be one of our most sensitive parameters. We see low reduction on the litter cover from thinning operations, as long as they do not do any burns afterwards. But after wildfire, the litter cover is removed, but you end up replacing it with an ash layer, which has maybe some of the same properties of it. And I'll discuss this result in more detail. And then if we think about what happens over 20 to 30 years after you've had some type of thinning, that it takes about 20 to 30 years for the soil to grow back, and that those are results from the Forest Health team at SNAP. And in wildfire, you still will have vegetation recover during the same time period, but without some type of intervention, most of the burn areas will come back initially as shrubs. So I want to focus a little bit on the thinking about what happens on this duff layer in terms of how it affects infiltration. Because if you have less infiltration, then you'll end up decreasing the yield out of your watershed. So if we think about a step topography, which I have in this top profile here. In the steeper slopes, they tend to be bare with little duff, and then you end up having forest duff accumulating on the flatter areas. Those are also the same areas that water tends to flow into and that you get some infiltration. So if you have duff in those areas, you get more infiltration, Um, and if you have no cover, you'll get a lot of evaporation coming out. Um, so you end up basically ending up with less yield because of the higher evaporation. After wildfire, if you only end up with a thin ash layer, you will and your it will reduce the evaporation significantly. But if you have um, hydrophobic um, soils, you'll end up with less infiltration. And if you end up with a very thick ash layer or litter layer, and that's what you see in the lower ground, you'll end up with, including some on the slopes, you'll end up with more infiltration and less evaporation. And that would be the bottom scenario would end up with a scenario that would provide the most significant water yields from your basin. So we did some um, um, uh, modeling, looking at whether if you had 90% soil cover or 10% soil cover. And so what you can see here is what I have is percent of precipitation converted to runoff on the y-axis, and then I have three scenarios. Pre-treatment. So pre-treatment, we haven't done anything with soil cover, so we get roughly about 50% of precipitation converted to runoff in our system. If you remove the vegetation and 33% of the vegetation, and we keep the soil cover, we predict that we're getting yields increase from 51% to about 59%. That gain actually decreases if you don't have any soil cover. So you start seeing below 50% conversion of precipitation to runoff. If you remove more vegetation, so 66% of the vegetation is removed, we see runoff gains of over 60%. But if we don't have that litter layer there, we're suggesting that you actually, even though you won't, because of the evaporation from the soil, you'll basically just be at pre-fire suppression levels of runoff. So you don't really get much gain for your vegetation removal. Now, taking those results, we want to move them up into the fire shed scale. And this upscaling process provides its own sets of challenges. We have a small 1 kilometer to 2 kilometer square kilometer basin, and now we would like to upscale the results from this basin into to a 40 kilometer squared basin. We decided that, so if we can think about that, we still have the same processes occurring on the larger landscape, and we're looking at where we think the biggest bottlenecks are in our model, and we think it's still the amount of water that infiltrates into the soil, and then if there's any any water that gets down below the soil layer into the weathered and deeper bedrock. So we looked at the two factors that we decided to focus on were how soil type varies across the larger fire shed and also how geology varies. And then how we approach them to look for similarities for scale up is that we have taken hydrographs from two gauged basins, the smaller scale basin and the larger scale basin, as well as we've been looking at how important geology was in constraining or if it affected the way the hydrograph behavior. And here what I have is a geological map, a fairly coarse scale geological map. We actually ended up using more finer scale maps for our modeling, but this one they weren't very pretty to look at. This one looked much better. So just to give you an idea of where the main um, geological formations are, so we have two in our last chance basin. The shoe fly complex, which has basically low groundwater storage potential and is not very conductive, and the Miocene-Pliocene, which has much higher groundwater storage potential. Here's some characteristics of them, and if we can compare the two of them, um, let's start down and looking at the bottom, the gauge basin that we're looking at, which was going to be the North Fork of the Middle Fork of the American River. And it has about 78% shoe fly complex and about 17% Miocene-Pliocene. Now, if you look at our two basins here, we have for bear trap, which is our treated basin, we have about 69% shoe fly complex and about 31% the Miocene-Pliocene. And Fraser, we have about, is quite different than bear trap with considerably more Miocene-Pliocene and less shoe fly complex. So we expect more water yield from Fraser. And then if you look at our fireshed average, it looks very much like the North Fork of the Middle Fork of the American River with roughly about 76% shoe fly complex and 24% of the Miocene-Pliocene. So here we're comparing how well do our three gauge basins correlate. And so we're looking at Bear Trap headwater, Fraser headwater, and then the North Fork of the Middle Fork of the American River. Typically, the North Fork of the Middle Fork of the American River has significantly more flow in it, although we do see in the wintertime some more peaks in the small basin. They're also higher elevation, so our smaller basins, higher elevation for their unit compared to the overall larger basin for the North Fork or the Middle Fork of the American River. But if you look how well our flows correlate, when they occur and typical magnitude correlate extremely well with correlations of above 97%. Also, if you start looking at what happens during low flow recession, from the headwater, we note that it takes about 400 days to drain to reach the absolute lowest base flow. And if we look at the North Fork of the Middle Fork of the American River, what we see is that it takes about 430 days to drain. So very similar characteristics for both this small headwater basin and this larger basin, which for us argues then their geology is not exactly alike, but geology is not going to be a limiting factor in doing this upscaling. So that's where we are now. We're basically feeling confident as we're moving forward to do our upscaling. We have our preliminary results on the forest treatment's impacts of water through snow, moisture, and stream flow. The treatments, we might not see much of an effect of the treatments because of the unfortunate timing of doing our treatments during a very low flow year. But we're still looking to see if we can capture some of the behavior in terms of what's happening in terms of the soil moisture response. Our sediment movements that we're seeing show periodic episodes. And basically, we see most of the movement, at least of the suspended sediments, were the first autumn rainstorms. And because it seems to be a sediment-limited system, it decreases through the winter and spring. Our model simulations show that water yields depend on both the amount of vegetation removed and the remaining soil cover. And so those are the two parameters that we're focusing on right now. And that we feel comfortable that we're going to be able to upscale our headwater catchment um, observations to the fireshed basin ones, given using a hydrograph similarity approach. And these all results are preliminary because we have not incorporated the LIDAR analysis of the removed vegetation from the treatments, and that will be processed and used later on this summer. Thank you very much for your attention.